Hello, in today's video we're going to be talking about single displacement reactions. So this is something different than we've seen before. So in order to understand or identify what a single replacement reaction will occur, if one will occur, we need to look at a table that's given in your textbook. And this is in chapter 4.6, I believe, of your textbook. It's either 4.5 or 4.6 of your textbook. And you'll see a chart that's very similar to this. This is your reducing agent strength. So as we increase, as we go up the table, the elements that are higher on the table are better at becoming a reducing agent than those that are at the bottom. This is a good thing. If gold was a good reducing agent, AU is gold. If that was a good reducing agent, your gold rings or earrings, if you got them wet, they would fall apart. But we know that gold can last for a really long time, and that's because it's not a good reducing agent. So let's see what happens here. Let's take a reaction between aluminum hydroxide and, so this will be aqueous, this is a strong base, and we're going to react that, or try and react that, with lithium solid. And we're going to try and predict if a reaction does take place. So let's see this. Lithium can potentially be a cation, it's a metal. Here the aluminum is already a cation. So what we want to see is if lithium can kick out the aluminum and replace it. So that's what a single displacement reaction is. The solid cation, most of the time, will be trying to kick out the cation of your aqueous solution. Now, how do we know which one is better at this? Well, if we were to assign oxidation numbers to these, each of these elements that are present here, and we were trying to make the aluminum hydroxide, we would see that aluminum is acting as a reducing agent. Now, how is that possible? What is a reducing agent? Remember a few videos ago we talked about reducing agents? A reducing agent is something that is able to give up electrons and reduce your other component. So in this case, aluminum, we know that the aluminum has a +3 charge, a +3 oxidation number as well, so it was willing to give up those 3 electrons just so that it could form an ionic bond between the hydroxide. Now lithium over here, its oxidation number is 0, it's in its natural state. However, lithium is much better at giving up its electrons than aluminum is. Now how do you know that? How do we know that? We go to this reducing agent table. We look for the higher up the list, the better they are at giving away their electrons, the better reducing agent they are. So if we look at aluminum, it is right here. But if we look at lithium, that is all the way at the top of the list. Lithium has the best ability of any of these elements to give up its electron and act as a reducing agent. Since lithium is higher on the list than aluminum, the aluminum gets kicked out of the solution and the lithium takes its place. So we end up getting lithium hydroxide, which is aqueous, and what happens to the aluminum? It gets kicked out, it crashes out as a precipitate. So it is a solid over here. So we can balance this equation. I leave that up to you guys. It's not a difficult not a difficult procedure to balance this equation. However, the aluminum went from a 3+ to a 0, and the lithium went from a 0 to a 3 or to a plus. So we can see that this is a redox reaction. We can see that the lithium was a stronger reducing agent than the aluminum. That's why it kicked it out. Okay? So that's an example of these single displacement reactions. We can do another one. Let's try reacting copper solid with calcium hydroxide. I'm going to stick with the strong bases because they're an aqueous solution, but this can be any type of an ionic compound that's aqueous. Okay? So here we have to see which one is better at being a reducing agent. Calcium, in this case, is a 2+, it can give up 2 electrons. Copper over here is in a 0 oxidation number. So now we look. Copper is way down here at the bottom. Calcium is way up here at the top. Calcium is already the better reducing agent. So in this case, it's already in solution. Copper is not strong enough, not a strong enough reducing agent to kick it out. So this ends up being a no reaction. if the element that's higher on the list is already in solution, no reaction proceeds. Okay? So we can talk about these, we can go through this list a lot, do a lot of different reactions, but now you can predict if a reaction is going to take place. We do these kinds of reactions a lot of times in like car manufacturing. Chrome plating, aluminum plating, gold plating. We do that kind of stuff using this very similar types of equation. Maybe not the gold plating, but definitely the chrome plating and copper plating we can use for this type of reaction to produce that result. So if you chrome plate your tailpipe or something like that, if you're a Harley person, then you can use a process kind of like this. Okay? So that is our reducing agent strength. We also have it for our oxidizing agents, which in this case we're only going to be dealing with halogens. The strength of the oxidizing agent goes according to size. So we know that as we go down the periodic table, the size increases and the oxidizing agent strength decreases. So here, if I have Cl2, which is aqueous, I'm going to have bubbled Cl2 into water. I'm going to try and add that to HBr, which is an acid. Okay, that's aqueous as well. We want to see if the Cl2 is a better oxidizing agent than the Br minus. And according to this chart, it is. What that means is the Cl will kick out the Br out of the solution, HCl, aqueous, and we will actually get gas coming out of this, which would be Br2. So this is a very similar process to the table that I showed over here for the reducing agents, but this is the oxidizing agents, and we're only going to be dealing with these halogens in order to identify the oxidizing agent. So if it's more to the left of this table, it'll be better at kicking out, be better at an oxidizing agent as an oxidizing agent than something that's to the right. And with that, that is all I want to talk about. We're going to be performing a lot of different equations tomorrow in class. Have a great night. I will see you all in class on Friday.